Hello and welcome to our webinar. This is John Morgan. I'm the marketing manager here at TMC. I'm glad you could join us today for our webinar. Actually, this is part 2 on optical table vibration control systems for photonics applications. Presented by Mike Georgalis, our national sales manager for North America. If you missed part 1, you can watch the recorded link, which we'll send out. And also at the end, we'd like to take questions. So if you have questions, please type them into the field on the right and we'll address those at the end. And right now, I'll turn it over to Mike.
Thanks, John. Good morning, good afternoon, good evening, everybody. My name is Mike Georgalis. I'm the North American Sales Manager at TMC. And this is part 2 of our optical table vibration control systems webinar. So a quick review. Remember, week 1, we talked about the top, basically. You have a 2-part system. You have your optical table top, and you have what supports it. So week 1, we did a quick overview of the types of photonic applications we see a lot. We did a sort of a crash course in floor vibration. We talked about what kind of requirements you want to see in a tabletop for damping. And then we also talked about performance as well. So we kind of did a deep dive into optical tabletop performance. This week we're going to talk about what's supporting your optical tabletop. So we're going to do a quick definition of types of isolation systems, the kind of things that you can actually put underneath your tabletop, because they don't, they need some. There's gravity. They don't just sit on the floor. We talk about combining systems. So you see sometimes there's combination systems, which is going to be an interesting part of this. We're going to talk about planning, and we're going to go over an interesting case study for an active vibration cancellation system. When we talk about types of isolation systems, these are the supports of underneath the table, and we group them into 3 types. We group them into rigid supports, which have no isolator at all. They're designed to be a stiff and damped, usually steel support. And what we're shooting for is a transfer function roughly 1-to-1 of what's coming from the floor and what's going to be seen on the table. They really don't provide any. And they are going to have some of their own resonant frequencies, which can be measured and seen. Passive isolation systems, we're going to define as anything that is using not active feedback control. Usually it's mechanically regulated and numerically regulated air systems or springs. They're usually pretty soft springs. They've got low resonant frequencies, around 1 to 2 hertz, and some of them have self-leveling capability. So that would be something like these systems here, these sort of piston systems. They're very, very common for optical tables. And then we're going to talk about active isolation systems, which take a few different forms. But some of the ones that we're going to focus on today are piezoelectric cancellation systems versus non-piezoelectric systems. But also we're going to dive into what happens if you put an active system underneath a passive system, and you get these hybrid systems. And before I digress too far, I want to talk about a question that came up last week that I thought was interesting, and I decided to add a slide about it. And it was about loading on your optical table. And after talking with our sales manager, Ken McKay, who was also on the call, I figured I'd add in something about supporting your optical table and where do you want to place your supports. So this is overly simplified, because as you guys probably know, optical tables can be made in all sorts of different shapes and sizes and lengths and widths. But in the case of a very simple example, like a 4-point support table, what you want to try to do is you want to try to support the table at points where the deflection of the table is the least. And what we have here is 2 points where you can really support a table. You have what are called the Airy points and the Bessel points. And we recommend that your table supports are placed at what we call the Bessel points. And here's a really nice graphic I found on Wikipedia that kind of describes that. Is any structure is not infinitely rigid, but as you support something, it's going to sag under its own weight. And if you support it at its what are called Bessel points, you get the least amount of sag, you get the closest approximation of a straight line when you support it at these 2 points. So it's something that you really always want to be looking at. when you're trying to decide where to support your optical table. But that's not the only thing. That's for an unloaded table. It's going to be greatly influenced, and your performance of your table is going to be greatly influenced at the center of mass of the payload. For example, if I have a large laser, a large cryostat on one end of the table, and all my mass is here, well, that's going to affect the deflection of my table. So you might want to ignore the Bessel point equation and just support it directly underneath the mass. So when you guys work with TMC or really any manufacturer of tables, and you're trying to figure out how to configure your support structures, it's really important to look at your payload. And if your payload's got some high center of gravity items or high items that are high mass that are on it, you're going to want to think about where you're locating your points. When we talk about isolators, we're really just talking about springs, and in this example, I'll talk about a very simple mass-tuned isolator, mass-damped isolator. And the key thing when you're looking at something that's an isolator is what we call a transfer function, also known as an isolation factor. And it's a ratio of the noise, the motion that you have on the floor to the motion that's sensed on the payload. And so you can actually, it's a unitless number, and you can get these, and you can really get a sense of where the resonant frequency is, and then how many dBs or how many times isolation you can possibly get. And a simple, mass spring damper has a curve that is going to amplify at some frequencies, and it's going to isolate at some frequencies. And here's an example of a theoretical one with a resonant frequency of this. We have a line here at unity, and anything above the line is considered amplification. Anything below the line is considered isolation. And when you look at this theoretical mass-tuned damper system and how it performs to how its transfer function looks, you can see that a completely undamped system is going to have a very high resonant frequency. So there's no damping in this one, and you're going to be having a amplification of what's coming in from the floor of roughly 100 times. And then you're going to have a quick roll off and have and really good isolation at higher frequencies. But then we started adding damp to these systems. So we started putting maybe fluid or some kind of friction-inducing component in here. And what that's actually doing is that it's restricting the motion, but it's also creating, in some sense, a mechanical short. It's allowing more and more energy to transfer to the payload. So there's always a trade-off. And so the more motion you restrict, the more damping you put in there, the more energy gets transferred into the payload. And what you see here is a damping of the resonance frequency, but here at a Q factor of 10, at a damping factor of 10, but then you follow this line out and you start to see degraded performance at higher frequencies due to that friction, that internal mechanical resistance, allowing some more transfer. And the more damping you have, like a Q factor of 3, the worse, the lower resonant frequency you have, and the less isolation you get at higher frequencies, until you get to, say, the critically damped state, where you've got no resonant frequency. So there's very restricted motion, but you're also looking at a much higher cost for your isolation at higher frequencies. You're isolating a lot less at higher frequencies. Passive vibration isolators, like the curves, like the piston type isolators we mentioned before, or springs with oil around them and things like that, even rubber elastomers and things like that, they all follow this sort of rule where there's a resonant frequency and then a roll off at higher frequencies. And one thing that's always true is that they're dependent on mass. So for a good example is your car spring. And if I'm pressing on the bumper of my car, I can drive it at roughly its resonant frequency, just roughly 2 hertz. It's going to go up and down 2 times a second or so. And it's highly damped because you have the shock on there. You've got that oil-filled piston that locks into your chassis, and that's helping that car not bounce up and down forever when I go and push on it. But what's interesting is if I went to a junkyard and I asked the folks at the junkyard to give me a spring from the car, they'd give me this large coil spring, you can probably imagine it, and I would try to press it down, but I wouldn't be able to, and I'd flick it with my finger and it'd probably resonate at an audible frequency. And that's so interesting because here you have a steel structure that's unloaded and very, very stiff, and it's got a very high resonant frequency, and I can't push it. But when I load that with the mass of a 1-ton car, well, it's very, very easy to push, and it has a very, very low resonant frequency, around 2 hertz. So, so I thought that was a pretty good example of how, you know, mass changes, or resonant frequency can change with mass. It can be very, very well pronounced when you use a car spring as an example. A lot of these air isolators, like a gimbal piston style isolator, they're actually sealed chambers. So you've got this piston, it's floating on air, it's in a sealed chamber. And one weakness is that they could be affected by the ideal gas law, PV equals nRT. So say the pressure in your room suddenly increases due to the probably a pressure drop due to the air conditioner coming on. Or somebody opens the door real fast and there's a big change in pressure in the room. Well, these pressure changes can actually cause the gas in your air isolator to want to expand or contract to match the pressure outside. So it's going to want to expand, and that can actually induce vibration. So there's a weakness there with these air isolators that you got to watch out for. And the performance of an air type isolator looks something like this, and it's really not that different from the curve, the theoretical curve that I showed before. Here's an actual product that we make called the gimbal piston isolator, and you can see that it has a red curve. This is the vertical transmissibility, or the transfer function, where it's got roughly a 1 hertz resonance, and it drops off very, very quickly. And then if you add the damping fluid to it, you get what we call a max damp isolator, which we patented back in the 90s. You can see that it lowers the resonant frequency, shifts it forward a little bit, but then you pay the cost of less isolation at higher frequencies. And the same pattern is observed horizontally. And so passive isolators are all good way to support optical tables. And if you have no sensitivity at these low frequencies where these isolators are going to be resonating, then you're probably okay. So we see a lot of optical tables out there supported by vibration, by passive systems with resonant frequencies. Active vibration cancellation systems are kind of your next step up for isolation. And what we talk about when we talk about an active vibration isolation system is something that actually has to have 3 components. It has to have a motion sensor, it has to have a force actuator, and it has to have some sort of control loop. And these 3 things are really, really important because if you don't have one of these, then it could be considered active in some ways, but it's not truly active because there's really no force actuator. Like a self-leveling system isn't necessarily an active system. It's a closed loop control system, but it's not necessarily an active system. It's not really actively actuating against the sensor. It's really just sensing with the leveling arm the position of the table, and then that leveling arm's telling will either open or close an air valve. So there's really no control actively. It's a motion sensor controlling a valve. So be careful because a lot of folks will call an actively leveled top something that is actually not an actively controlled top. We have 2 types of active cancellation systems. Once you start getting these components, these sensors and these actuators and these control loops all together, you can start putting them together in different ways. And there's really 2 ways that I want to focus on in this presentation. You have a serial type active control system, and you have a parallel type active control system. TMC makes both. We make serial type systems to support payloads from underneath and cancel out floor vibration, but we make parallel type systems to create to cancel out motion on the payload, and it has to be a known motion on the payload. So usually it's like a moving stage or something like that. So let's start talking about parallel type systems. And a parallel type system it has an architecture over here on the right hand side. Here's your mass. So this might be like your optical table, for example. And in a parallel type system, you'll have your sensor on the optical table. And then you're going to have your optical table supported by some load-bearing isolation, a passive isolator. So it's like a spring or a piece of rubber or very often a pneumatic piston-style isolator. But then you have your control loop, which is required, and then you have a force actuator. And then your force actuator here is going to be a usually some sort of linear motor. That's the most commonly used, or a voice coil motor. That's the most commonly used type of force actuator that's acting on the table. And what it tries to do is it has motion on the payload. That sensor is going to send a signal to the force actuator, and that force actuator is going to try to expand and contract and exert a force on the table to try to cancel out whatever to basically be equal and opposite to what is being sensed by the sensor. It's actually not too different from the shaker type systems that we explored regarding active damping last week. But except that the shaker is not internal to the table, the actuator is outside of the table, and it's actually pushing against the floor as opposed to just living in the table, generating its own energy. But I digress. One of the things that you're always going to be dealing with a parallel type system is the fact that there's always going to be an input from the floor that's amplified commensurate with the resonant frequency of whatever is bearing the load of the system. So say this is a soft spring and you've got a 2 Hertz resonance. Well, that 2 Hertz resonance is always going to be amplifying floor input and always feeding into here. And so right off the bat, you are spending a lot of your cancellation energy canceling out the system's own resonance. And then you have some limited bandwidth available for everything else that's going on top of the system. See, the system can't tell whether or not it's sensing floor vibration or payload vibration, so it tries to cancel everything. And that could lead into a system that might have stability problems. And in order to get better stability in a parallel type system, you find that you need to start to reduce its effectiveness at certain frequencies. So it takes a fair amount of tuning to get one of these systems to really perform at a high level, and therefore they fall out of tuning. They can tend to fall out of tuning very often. What we see parallel type systems for, one of their main advantages is the fact that they lend themselves very, very well to what we call feed-forward capability as opposed to feedback capability. Their feedback performance as far as floor vibration control is so-so, but their feed-forward is really great because a linear motor is very, very powerful. And what you do when you feed forward something is you have a known condition on the payload. Maybe it's a motor turning at a known frequency, or it's a stage moving back and forth with a known mass and acceleration. Well, you can get a parallel system to counteract the vibration induced on the payload using that known input so that it can actually start to react to a known input before that input actually starts happening. So there's a real strong advantage when there's known motion on the payload to using a parallel type system to cancel that out and keep the payload still. Serial type systems have a little bit of a different architecture. These guys are used, these guys introduce a smaller component, a separate component inside. We call it an inner mass. And keep in mind, this is a one-dimensional free body diagram, but this architecture exists in 3 dimensions, which once you combine this architecture with several isolators, you end up with 6 degree of freedom systems. Well, here we have your mass again. We'll call this your optical table, or maybe this is a set of legs on top of and then an optical cable on top of that. It could be anything. Doesn't really matter. But inside the serial type system, you have, and I'll go more into stacking systems at a later slide because but let's just say right now it's supporting a rigid granite block. And you have your passive isolator, and you have your inner mass, and on top of your inner mass, you have your sensor. And that sensor is providing feedback and then sending a signal to the actuator that's equal and out of phase to what's sensed in the sensor, and you're trying to keep your sensor value at 0, just like any point of any active cancellation system is trying to do. And so there's this fundamental architecture difference, but there's also a difference in the types of components that are used. For example, in the serial type system, the passive spring here, it's going to be, by necessity, a high stiffness spring. So we're talking about an elastomer mount with a higher resonant frequency, maybe 15 to 20 hertz. And that rubber mount serves an important function because what it does is it allows any noise that's on the payload, whatever's happening up here, stage is moving, people walking, people knocking and rapping on the block, that's going to get filtered out by this system, and then very little of that energy is going to get sensed by the sensor, and then have to be fed into the feedback system. Also, what's interesting is that our force actuator is a piezoelectric, a ceramic piezoelectric crystal, which is a device that will expand and contract in response to voltage that's applied to it. And what's so interesting about piezoelectrics is they, unlike a linear motor actuator, can be load bearing. So you have your piezoelectric actuator bearing the load of the inner mass, which is then bearing which then has a spring on top of, which is bearing the load of the entire system. So you have a load bearing stiff actuator, which is different from a load bearing soft spring and non-load bearing actuator. And what that allows you to do using these stiff components is to really take out those low frequency resonances that are inherent in a parallel type system and support your entire system using stiffer high frequency components. And there's a real advantage to that when it comes to floor vibration, because that frees up a whole, there's really no amplification, or very, very little amplification of floor noise coming in here. And also, there's very, very little payload noise coming into the inner mass. Therefore, the sensor is free to really cancel out only what's sensed on the inner mass, which is only what transfers through the stiff actuator that's supporting it. And that provides the ability to provide much, much better active vibration cancellation because you've got no low frequency resonances feeding into the control system. And you can provide much better performance that way. And here's the difference between serial type and parallel type curves. You can see both already are much more outperform passive systems. Remember, a lot of our undamped passive systems and even our critically damped passive systems would be seeing a resonant frequency that would spike up here, and then, you know, if it was well damped, you'd see a good drop off. But if it was critically damped, you'd see a resonance maybe coming up around here, but then you see much, much lower high frequency isolation for a system like that. But when you compare parallel versus serial type, you see here in the red line, the parallel type transmissibility, where you're amplifying around 1 hertz, and then not really getting really good performance until, you know, 5 or 10 hertz, 5 or 6 hertz. And then you start seeing better performance once you get higher frequencies, once the passive portion of the architecture, sort of that contribution from the passive springs, high isolation, that high frequency starts to kick in. By contrast, and the reason is you're always going to have that internal resonance of the system. The serial type system has no low frequency components. So you start to isolate where this system is resonating. You're already isolating at about 50%, and you get a good roll off after there. Of course, there's going to be some very, very, very low frequency isolation amplification here in a serial type system. This is so low frequency, it's actually very rarely registered on any sensitive device. And what's interesting about that is that it's not a mechanical resonance. That resonance is not due to soft springs in the system. It's due to the effective electronics and the bandwidth, the noise floor of the system. So there's an electronic limit we start to run into there that provides this, but that's really not. That's actually something that's never found to be problematic. It's so low, it's actually considered to be more like rigid body motion. Okay, So you've got two types of isolation systems, and you've got your reactive systems and you've got your parallel systems. And what happens when you start combining, well, you've got active systems, you've got passive systems, and you can combine them in several ways. You can put an active system on top of an active system. You can put a passive system on top of an active system, or you can put a passive system on top of a passive system. And there's a lot of considerations, but really, when you come down to it, you really need to do one of two conditions. You need to have a separation of mass or a separation of stiffness. And in a separation of mass, this is an example where you might have a large inertial block, like the plinths that you might see at some locations. And actually, I'll talk about that in the next couple slides. But if you put if you have systems of similar resonant frequencies, for example, here's a soft spring, an air spring system, and then here's, K is the spring constant, and here's another K similar to the K that's stacked on top of it. If you put a large mass, like a concrete block, in between the two Ks, what happens? Well, you don't necessarily, if that mass is sufficiently large enough, then those two systems, they won't couple with each other. They won't necessarily start playing off each other and causing problems with each other. That's what you want. But you're not gonna, but you're still going to have a summing of the transfer functions. So you're gonna have, really you're gonna have this system resonating at some frequency. Then you're gonna add that resonance to this resonance, and that's gonna resonate at some frequency. So you're gonna have really, really bad low frequency performance if these are soft springs. But then you're gonna have awesome high frequency performance because of the summing of the transfer functions. The other way to do it is with a separation of stiffness. And separation of stiffness is used really can only be done with active serial type systems and passive systems. Because what you see is, what you've got here is, for example, a soft spring. And then you've got maybe an air isolator. And you've got a spring of much higher stiffness, which is what you'd see in a serial type active piezo-based system. And what's in between them doesn't really matter, because these two springs are so dissimilar in resonant frequency, they're not likely to start to interact with each other. And then you get another summing of the transfer functions. You get the resonance of this soft spring, and then it's isolation, but then you get the lack of resonance of the stiff spring active system, for example, and then you get summing of the and then less of a roll off at higher frequencies. I should also add that you could put an active system on top of an active system, and that would work because most of the active and that would really only work in a case where it's an active system that is supported by a soft spring, because most of those soft springs I had mentioned before are typically low frequency springs. You've got that impedance mismatch that you're looking for. And also, if this active system on this top portion is canceling payload motion or doing all sorts of other sorts of energy-inducing activities, it's important that you use a serial type system below it to filter out the noise that this active system is making. If this was an active parallel system on top of an active parallel system, well, the system down below here and the system up here would have a lot of problems, because you'd have a matching K with not a lot of mass in between of them, but you'd also have the sensor on this payload sensing everything that this system is trying to do to cancel out what this system's doing, what it's sensing on this payload. So you really got a compounded problem. So I really recommend never stacking parallel systems on parallel systems. It's really a recipe for disaster. Okay, so let's talk a little bit more about stacking systems. And here's a really cool example. Here's a plinth at a leading US research university. And what we have here, we have an optical table here placed on this isolated plinth. And I'll go here to show a better photo of the plinth. It's a classic T-shaped plinth weighs about 25,000 pounds and is supported by pneumatic isolators. And when we walked in here and we saw this application, what we saw was that the researchers actually, and I'm sure you guys have seen this before too, have deflated the isolators inside the upper optical table. And they did that because they were having a low frequency problem. They weren't having coupling problems. It's not like this table was bouncing up and down and then this table was bouncing up and down and they're fighting each other and oscillating and all that garbage. No, they had a good separation of mass, but the resonant frequencies that were low frequency were summing, and they were summing to a point where it was so bad that the resonance from the 2 hertz in the floor or the plinth here was plus the resonance of this one was so bad they had to deflate these isolators. So it became kind of a useless second stage of the system. And here's what we found when we took actual measurements here. And it's exactly what we would expect. You have a red floor, which is down here. These are actual data. This is actual data in meters per second, RMS, 1/3 octave. And so it's a pretty quiet floor. It's a VCE floor. It's pretty quiet. And when we measured on top of the plinth, we saw exactly what we would expect those plinth isolators to show. It doesn't matter how massive your plinth is. It's still supported by something floating that's resonating. And you've got this 1.6 hertz resonance, and then a really good roll off at lower frequencies. But then we took a measurement on top of the tabletop. So the third measurement we took was up here. And what we found was, well, pretty much what you would expect. Rigid body behavior, roughly 1-to-1 transfer function between the top of the plinth and the top of the table. And then when we started measuring the tabletop, it was deflated. So we're starting to see a lot of the higher frequency resonances coming into the table, which is also to be expected. And this could be from noise that was generated on the table, or it could be noise that was acoustic in the facility. It could even be some transfer from, well, it's probably not transfer. It's probably more due to resonances that are above the table and resonances of the rigid legs themselves. So if it was coming up from the floor, we'd see it. In the floor data, in the floor data, which is actually the blue data, not the red data. I'm sorry if I kind of went through that, but I guess the key takeaways are: doesn't matter how massive your plinth is. If it's supported on isolators, it's going to resonate at the frequency of those isolators. And so we knew that there was this need over time to get more and more isolation for optical tables, and the plinth just wasn't cutting it, as I had exemplified before. If you want to put a floating table on top of a floating plinth, you really don't win. You really don't gain much. So the next thing is, well, why don't we try to put our floating table on top of an active cancellation system? And this is something we started to see happen sort of around in the early 2010s, 2009, 2010 timeframe, where the floating isolators inside of a table really weren't providing enough. And what they wanted to do was, what customers started wanting to do was put it on active cancellation systems. So we developed these sort of floor platform cancellation systems to provide this combined transfer function. And these are what we see when we see, the different types of transfer functions. For example, you have a passive air isolation system. So the table alone on the floor, as I had mentioned before, is going to have a resonant frequency and a good roll-off. Say I put some sort of air handling system on there, or say I went in here and I bolted a linear motor to the side here, and I put a sensor on top here, and I created a parallel type active system. Again, there's no active system down here. Well, that would give me something like this. I might be able to cancel out that resonant frequency and damp it out using that feedback control. And in the best case scenario, then my higher frequency sort of matches the higher frequency of the high frequency roll off of my air isolators. Well, that's great, but I'm not really isolating at low frequencies here. So what's the next thing we try to do? Well, we try to do a serial type active cancellation system. So when we look at the different ways to do this, what I might want to do is what I would do is get my maybe, I'm sorry, if I keep these deflated and I keep them rigid, then what I might want to do is put it on just active air isolators. So if I put it on active air isolators, or I'm sorry, on active piezoelectric isolators, I get just the benefit of the no resonant frequency of the active serial type isolators. But then, as I showed before, we really don't have a great story for high frequency. But if you combine the two systems and you do what you can potentially get is some coming back of the resonance. So if I now inflate these isolators, so I've got inflated isolators on this floor platform, I have a little bit of a trade-off because I have to deal with that resonance coming back into the system. So adding on to this curve, I have the resonance, but then I have the isolation of those isolators. So again, I have a nicely combined system, but then I have this resonance that I'm dealing with. Well, that was the sort of first step of this. What we did subsequently was we noticed we had this problem. We had this input of the air isolators kind of canceling out the good performance of our active systems underneath. And we developed a product called the laser table base, which really kind of packages this all together, and it takes into account the fact that we have these this resonance as part of a second stage of the system. And when we tune the active isolators to kind of really hone in on that resonance, and then we tune when we add some damping fluid and start to dampen out that resonance to these, you can provide a system that actually doesn't necessarily show this performance. When built correctly and packaged together, you're still isolating at low frequencies quite a bit. And so this is sort of this culmination of some of this work that we had about 10 years ago, where people were putting optical tables on top of isolation systems. Well, if we put it all together, you tune the system properly, and you manage that resonance of the air isolator properly, you can actually still get really great performance. That's sort of the best of both worlds. You see this really good isolation up to 2 hertz for horizontally and vertically with very low resonant frequencies, and then really also good high frequency cancellation. So one of the things I also wanted to talk about is planning for vibration control. I'm going to switch gears and not really talk about about isolation systems themselves before. We're going to go into vibration control and planning, and then a case study. So there's a graph from a very interesting study that was done back in the early 2000s, and it took place at a facility that was newly built. And when somebody's going to go out and they're going to build a new facility, they might specify the types of equipment that might go in there, and they might say, well, this facility needs to have a certain level of vibration when it's built. And in this case, that is what happened. And you can see here in the red line, after the facility was built, they went there, and it was done by Colin Gordon Associates, and they went in there and they took a measurement of the floor, and they saw what you would expect of an empty facility. There's some hump of vibration around 50 hertz, and then really not a whole lot of noise everywhere else. And that 50 hertz hump is probably due to the motion of HVAC systems and machinery and things like that in the building. When you go in there 14 months and 17 months later, now you've got a facility that has had all the people move in, all sorts of other equipment move in, and it's a busy, functioning facility. We've seen increase of almost 10 times of vibration at various frequencies. And so the takeaway is, it doesn't matter how quiet your floor is, there's always, especially in a new building, as time goes on, vibration rises. And this is also true at universities. You may have a nice quiet floor in a physics lab, but then there might be construction next door that causes problems for your experiment for some long period of time. Or worse yet, you're asked to move out of your nice quiet basement into the upper floor of another building, which we see a lot with our customers. And that is going to lead me into my case study of this ultra-fast optical spectroscopy experiment. So we had a customer in a lab, and this lab was actually a really nice, quiet floor. But the problem with this lab was they had really bad temperature and humidity control down there. And so they had to move into a new lab. The only reason, and so the problem with the new lab was while they had really great temperature and humidity control, they had a real bad vibration problem. So they traded temperature and humidity problems for vibration problems. The good news is that the vibration problems are solvable. And what we did there was we took a measure. I'll talk about that on the next slide. You know, over here on the right is a quick example of the water absorption lines of a silicon wafer. And so this is relative to the model that you would see, and you can see that the old lab, due to vibration and temperature control, much worse standard deviation versus in the new lab. So they actually achieved the temperature and humidity control that they wanted to get to in the new lab. But in the new lab, which the systems that were mounted on active cancellation systems, these are photos of the new tables, they actually couldn't provide us data, useful data, or actually take any data when the active cancellation systems were turned off. The floor vibration was so bad. Furthermore, they didn't want to, because the floor vibration in the new lab would cause misalignments of the components. So, so really, it was so bad there that you really needed this active control. And so what's the goal? When you're moving from a lab and you have a custom setup and you have a custom experiment, you want to try, and you don't necessarily know how much of a problem vibration is for you. What you really want to try to get to is something that matches your current setup. And so you take some measurements. You look at the old location, you look at the new location, and you try to do some modeling, and you try to think whether or not you can try to match it. And so that's what this data here shows. You have the solid lines here, which show the floor vibration in the new location. And then you have the dotted lines that show the floor vibration in the original location. And you can see right off the bat, the floor in the old location, the dotted lines, are much quieter than the floor in the new location. And this is probably due to the fact that this is an upper floor. And you start to see this very common 2 hertz to 3 hertz building resonance. And these are all X, Y, and Z, or side to side, front to back, and vertical measurements. So, so you have this low frequency building resonance in the new location. What we also saw is taking measurements of the tabletops. You saw something that really echoes what you would expect to see on the floor. You'd see, you know, the tabletop is pretty quiet. It's behaving relatively like a rigid body in the original location, and then you start to see the resonances of the supports. I should mention that the original tables were even in the original location. It was known that these tables, being on passive isolators, they were having a low frequency problem because of the resonance of the isolators, even in the quiet basement floor. So they already deflated these isolators, which is why you don't see a resonance peak here to the tables in the original location. But you do see resonances around these frequencies, which is probably close to the resonant frequency of a deflated table. And then here you have location 2, the table. So here we have, again, deflated tables in the new location with this, with the new active table. So I'm sorry, so this is actually the new tables. So in the new location, we saw some input of this floor resonance causing, you know, being knocked down by some percentage. But still that percentage was tolerable. So now looking at the table performance in the new location versus table performance in the original location. So the other graphs, I kind of took the data from the other graphs and tried to provide them the performance of the actual table. So here's the original tables in the original location, and here's what we saw. The floor. This is trying to show us transfer function data, and we're seeing roughly 1-to-1 transmissibility from the floor to the table. But at the new location where we have the actively canceled tables, we're seeing some really good performance. We're seeing, here's the original floor data. There's that resonant frequency we talked about in the new location. And then here's the tabletop data with the active cancellation system. It knocks it down, sometimes almost 10 times at this low frequency, and then really good high frequency performance. And again, the takeaway is, yeah, we weren't necessarily able to replicate the exact floor conditions in the original lab. However, we were able to take out enough of the problem vibration that they were able to still perform their experiments and then benefit from the new humidity and the new temperature conditions in the new lab. So this was actually a pretty successful install. So in summary and in conclusion, as photonics technology and research advances, vibration will increasingly become an issue. There are two factors to consider when selecting an optical table. There's damping and isolation. We spoke about damping last week, spoke about isolation this week. Increasing vibration is an unfortunate reality. You're going to move your facility, you're going to have construction and buildings being populated, increasing vibration over time. And if you really need to get to a place where you need the best vibration control, especially for photonics applications, you want to combine your active and passive systems to benefit from both the low frequency performance supported with a serial type piezo based system and the high frequency performance from the passive isolators. And that's the end of the webinar. So if anybody has any questions or suggestions for future webinars, feel free to contact or reach out.
Thanks, Mike. Yeah, and I'd say we have a couple questions. I would suggest that anybody in the audience, if you have any questions, type them in and we'll get to them. Mike, the first question was, does a piezoelectric serial type system help at all with noise generated by things on the table like a payload?
Yeah, that's a good question. Does it help? Does a serial type system help payload generated noise? And actually the answer to that is no, it does not. It's specifically designed not to. And the reason why is if you go back to the system architecture, you've got your stiff spring here, which is going to resist to some extent. So say I have something going back and forth and moving a lot on the payload here. That motion is going to get filtered out by this spring. But there's no actuator between the inner mass or the floor or anything acting on the payload to actually try to work against that. And so, yeah, payload noise is not canceled by serial type systems, but that's by design because you're not trying to cancel that payload noise. You're free to focus on canceling only floor noise, which is what makes them ideal for floor vibration cancellation.
Okay, thanks. Another question, if I have an instrument that already has a passive isolation system provided by the equipment manufacturer, is it safe to put this on one of your active systems, even if the original table isn't one of yours?
Yeah, it depends on how you're stacking them, but I would say in general, when you look at a stacked system like this or like this, where you have the active and the passive, the serial type system is designed to put something on top of it. And so if you've got, say, a scanning electron microscope or an atomic force microscope or something that's got its own passive isolators, or even if they're active parallel type isolators, it's totally fine to put them on an active serial type cancellation system. Where you got to run into trouble is if you've got, a laser table base like this, and it's got your passive system and it's got your active system already, and then you want to put another passive system on top of this. I would look at that very closely because you want to make sure that this table here has enough mass so that these isolators don't couple with whatever isolators are up here.
Okay, thanks, Mike. Maybe you can go to your last slide, just show your contact information. We don't have any more questions at the time, but yeah, if anybody wants to get in touch, there's Mike's contact information. We will send out a link to the recorded webinar. And thanks very much for attending, everybody.
Bye, thank you.